All right, welcome to your review video for cumulative test number 5. We're going to start today with a review of limits reading from a graph. So again, when we think about limit notation, we want to read this as the limit as x approaches 1 from the left of f of x. So here's my function f of x. And I'm trying to figure out as my x's get closer to 1 from the left, what is my intended height, or my y value, the height of the function. Where am I trying to get to as I get closer to 1? Do I care about what's going on at 1? No, not at this moment. I care about what's going on as I approach 1. So here's x being 1, and as I come in from the left on x, my y's are coming in and approaching 1. Coming in from this next one would be from the right. So what are my y values doing? They are approaching -1. And because 1 and -1 are not equal, my overall limit here does not exist because I don't have the same intended height from the left that I do from the right, and therefore that overall limit does not exist. So the next one, the limit as x goes to 4, well, here's 4, coming in from the right, going up to infinity. Now keep in mind that's me describing the limit. Overall, the limit does not exist. I'm not approaching anything, but I could describe it as infinity. Coming in from the left, I know yellow is not the best color to read, but we'll work with it. Coming in from the left, my graph is also going up to infinity. So overall, the limit does not exist, but I am approaching infinity. So the limit overall as x goes to 4, this is tricky, because remember, we can say the limit itself does not exist. I'm not approaching anything. However, because from the left and from the right are approaching the same version of infinity, right? They're both going up to positive infinity. You could describe the limit or use a descriptive limit of infinity. All right, running out of colors here. Let's erase this. So next one I have is the limit as x just goes to -2 overall. So here's -2. I have to consider from the left and from the right. Well, from the left, I'm going to 3. From the right, I'm going to 3. Good news, 3 is equal to 3. My limit or intended height is 3. The next one, the limit as x goes to 3. Well, here's 3. Coming in from the left, I'm getting to 0. Coming in from the right, I'm going to 0. Those are going to be equal with a limit of 0. And then the last one, the limit as x goes to infinity. Well, x going to infinity would be going that way. And it appears that I'm having a horizontal asymptote at 0. So I'm going to approach 0, but never actually get there. But my intention would be to approach 0. These last two are just a little review from function notation, f of 1. So if I go to x being 1, what is my output? I get -1. And f of 4, what is my output? That does not exist. I end up with a vertical asymptote. There is no value there. All right, that was a quick review of limits. Remember, you can go back to the actual unit on limits from a graph if you need more of a review for that topic. For numbers 2 and 3, find the domain, zeros, holes, and vertical asymptotes for each rational function. Write your domain in interval notation. If you do not have any zeros or holes, write none. So first of all, remember we have a rational function because we have the word ratio. So we are comparing two different functions together that create one rational function. And I want to start by doing some factoring so that I can read my domain. And remember, the domain I want to be of the function itself, so I don't want to cancel anything out yet. Okay, I want to leave everything just as I see it. So I'm going to have x plus 7, x plus 1. I think that's going to get me back to where I need to be. And I'm not canceling anything. I just want to read my domain right away. And my domain is going to be everything except for when x is 0, when x plus 7 is 0, and when x plus 1 is 0. So that means my domain is going to be -infinity until I get to -7. -7 until I get to -1, and then -1 until I get to 0, forgot a comma, and then from 0 until infinity. Okay, so my problem spots are at 0, at -7, and at -1. Next thing then, I want to think about my zeros. Okay, so I'm going to start canceling some things out. I'm actually going to jump to holes next, because holes are easier to read next. So when I cancel out my factor of x plus 1, I get a hole at -1. But then the next thing is I got to figure out when I plug -1 in, what do I get back? So if I plug negative 1 into what's left, negative 1 minus 1 over negative 1 times negative 1 plus, that's a 7. I end up with negative 2 over negative 1 plus 7 is 6, negative 6. I end up with 1/3. So that's my output for the whole. All right, so then my zeros, I'm going to use my canceled out function, my factored function, and I'm going to set the top equal to 0, because if I want to know where this whole function that's left over, x minus 1, x plus 7, is equal to 0, it's really going to be where the numerator is equal to 0. So if I put in 1, I get an output of 0. And then the last thing is my vertical asymptotes. And the vertical asymptotes are going to be domain problems or discontinuities that could not be removed, right? They're non-removable discontinuities. I couldn't get rid of this one and I couldn't get rid of this one. They were still left over. So I'm going to have a vertical asymptote when x is 0, and I'm also going to have a vertical asymptote when x is negative 7. Notice that my 3 domain issues, negative 7, negative 1, and 0, have all been classified as either a whole or a vertical asymptote. All right, for our next one, we are going to start the same way. So I'm going to start with my factoring, just so that I can have a better idea of what's going on with my domain. I'm not going to cancel anything out yet. Okay, I want to read it from the actual function. I just want to make it look a little different so that I can read a little easier. And this is going to factor into positive 4 and negative 3, so that I end up with that positive middle term. So looking at this, I'm going to have problem spots when this is equal to 0 or when this is equal to 0. So I'm going to have a problem spot at negative 4 and 3. Those are going to be my 2 discontinuities, which means my domain is all the good stuff. Negative infinity to negative 4 until 3, and then 3 to infinity. So I'm going to skip again down to the part that was finding the wholes. The wholes are going to be the part that cancels out. Remember, when you cancel from top to bottom, a number or a factor divided by itself is going to have a result of 1. So I'm left with 1 over x minus 3. So there is a whole at negative 4, because that part went away. When I take negative 4 and I plug it back into here, I'm going to get 1 in the numerator over negative 4 minus 3. So I get negative 1/7. Whole is a coordinate point, x comma y. So now in thinking about my zeros, I'm going to set my canceled out version, my simplified version, equal to 0. And I want to look for where the numerator is equal to 0. Will 1 ever be equal to 0? I don't think so. So I have no zeros, which my instructions said to write none. And then the last thing, those vertical asymptotes are going to be the discontinuities that could not be removed or did not cancel. So I'm going to have a vertical asymptote when x equals 3. Again, notice that each one of my discontinuities, negative 4 and 3, was then classified as either a vertical asymptote or a whole. All right, limits algebraically. Remember, our first method for a limit is always going to be substitution. So I have the limit as x approaches 3 of this whole function. So I'm going to try to substitute in 3, see what happens. 3 squared, 9. 9 times 4, 36, minus 27 plus 2. 36 minus 27, thinking 9 plus 2 gets me an answer of 11. All right. Next one, direct substitution. I'm going to try to substitute in. I'm going to end up with 4 squared minus 16 over 4 minus 4, which leads me to a result of 0 over 0, indeterminate form. So that means that there should be some algebra that I can do, some sort of conjugate, some sort of factoring, some sort of clearing of denominators, some trig identity, something that can help me to make this limit no longer indeterminate. So I'm going to look at this as a factoring route, and I'm going to say x minus 4, x plus 4 over 4 minus x. I still have my limit as x goes to 4. And this is kind of tricky because I see x minus 4 and I see 4 minus x. Those are like kind of close. Well, if I factor out a negative 1 from here, on the bottom I would get negative 1. That becomes now negative 4 and positive x. And hopefully we can agree that x plus negative 4 is the same thing as x minus 4. So when I think about canceling, my x minus 4 and my x minus 4 go away. So now I'm left with a brand new limit, the limit as x goes to 4 of x plus 4 over negative 1. Now when I try substitution, which failed me the first time, I end up with 4 plus 4 over negative 1, which is negative 8. Also remember, okay, that in trying to get these things to cancel, we could have factored out the negative 1 from the x minus 4, and those would have canceled just as nicely, okay? But you do need to make sure you adjust for that negative because it was not a perfect cancellation prior to that. The limit as x goes to 0, try some substitution. 0 cubed plus 5 times 0 squared minus 6 times 0 all over 0, womp womp, 0 over 0, indeterminate. So I'm going to look to see if there's anything I can factor or cancel. And in the top, I am in luck because I can factor out the x from each one of these terms. And now here I am getting rid of the problem spot, right? I just canceled out the whole from my rational function. Now I'm just left with a brand new limit, the limit as x goes to 0 of x squared plus 5x minus 6. When I try direct substitution, 0 squared plus 5 times 0 minus 6 gives me a result of negative 6. Number 7, I have the limit as x goes to 9, or x approaches 9, of the square root of x minus 3 over x minus 9. I'm going to try my direct substitution. And I end up with 0 over 0. So this one, I could try some factoring, which I will get to in just a minute. But because I see this square root, I'm also going to consider multiplying by the conjugate, that should be a 3, so that I can get my square root to become part of a difference of squares and to go away. So the conjugate I want is the square root of x plus 3. And if I multiply by that on the top, I got to multiply by that on the bottom to keep everything equal. So on the top, I know that I'm going to get a difference of squares. That was my whole intention. So the square root of x times the square root of x is just x, plus 3 root x minus 3 root x cancels out. Negative 3 and negative 3 and positive 3 is negative 9. And on the bottom, I don't multiply together yet, because the conjugate was to help me with the numerator. And so I want to be able to see my denominator, because here I am canceling out the problem spot from when I substituted in 9. So now I have a brand new limit. Limit as x goes to 9, 1 over the square root of x plus 3. When I try substitution, 1 over the square root of 9 plus 3 becomes 1/6, and that's my final answer. Those of you that are factor savvy, you guys have learned about the difference of perfect squares, but you could also do some sneaky factoring with this x minus 9. X minus 9 would be the square root of x plus 3 and the square root of x minus 3. Okay, you can check that by multiplying back. And then on the top, I just have the square root of x minus 3. Still have my limit as x goes to 9. Still have a problem spot. When I plug in 9, I get 0 over 0. I need to keep going. But here, I can cancel out these ones. Be left with 1 over the square root of x plus 3. Same thing I was left with here, not a surprise. I still get an answer of 1/6. So again, 0 over 0, indeterminate form. You need to find some way to keep going to evaluate that limit. I'm just about out of time, so I'm going to pause the video here. You can pick up with the next video to continue on with your review.